Yes, so thank you everyone and welcome to this last talk in this session where I would like to dive again into some technology. This time it's about measuring greenhouse gases. So I'd like to acknowledge the huge group of co-authors who made this particular super site I'm going to present possible. So first of all, what's the context of this? This is part of the so-called ICOS cities. Some of you might have seen ICOS cities logos throughout the conference. ICOS cities brings together and evaluates different measurement and modeling approaches, essentially to monitor greenhouse gas emissions from cities. The focus is really on having modeling, but also observations play an important role. And the overall project is a European project that supports the European Green Deal with the aim to develop eventually useful services for cities in support of assessing emission reductions. And eventually this could become part of the regular European infrastructure ICOS. So although that's the way into the translation of science, I really would like to focus on some basic developments that are done within this. So I will focus on the observational component only in my talk today. As part of ICOS cities, we had the great opportunity to establish 3 urban pilot observatories targeted to measuring greenhouse gas emissions in one large, Paris, mid-sized Munich, and the smaller city, Zurich in Switzerland. And in all those cities, we deploy a whole range of technologies that have been already used or are at the verge of being possibly used for measuring greenhouse gas emissions, including tall tower networks, roof, street level networks, also remote sensing techniques. And amongst them, there's also eddy-covariance towers. Specifically, Matthias made the call to have tall towers, so 100 meter plus, to have large source areas. And I will only focus on this number 4, those tall eddy flux towers, but they should be seen within the context of others. And the goal of those observatories is to compare different techniques. It's clearly an overkill to have all those systems deployed concurrently in a city, but we can actually compare and see which technology has which advantages and to quantify, but also to partition CO2 emissions into different sectors. And we would also not only say they are competitors, those technologies, there could be really synergies between doing eddy flux measurements that can infer flux ratios and tall tower networks on a 100-kilometer scale and see whether those synergies can be used to improve the model observational products. And eventually, some of the data sets could also be put aside and being used as evaluation data, as benchmarking data for other products. So those are the aspects. Now, coming back to the eddy-covariance approach, eddy-covariance has been used to measure greenhouse gas emissions from small subsets of cities, so essentially neighborhood scale. And what's the nice thing about eddy-covariance is it allows us to have high temporal resolution. So we can have emission profiles, how emissions change over the course of the day and over seasons. It also has been used already to derive emission factors for particular processes if we relate it to surface, let's say, traffic counts, for example. The EC approach, however, provides net fluxes. That means we only see total CO2, and we can actually not tell whether it's coming from traffic, stationary combustion, or big problem is, of course, the biogenic component. Maybe it's not a problem, maybe it's also a part of a solution, and we want to quantify as well what's the biospheric component, what is the effect of respiration minus photosynthesis. But the problem really is measured net fluxes. They do not allow for direct sectoral attribution of fossil fuel fluxes, and it would be desirable to separate, in particular biogenic versus others, but also between different sources. And so that's the motivation for this work. And the little picture here shows that nicely with those colored dots, that, for example, from the chimney to the right, there are purple compound emitted as well, and from the traffic, it is blue. And so maybe we can use not only there is or not, but the amount of co-emitted species to attribute this. And the technology that allows us to do this are new laser spectrometers that can concurrently measure many, up to 10 species here, a 7-species analyzer we are using that measures CO, NO, NO2, methane, N2O, and so on, concurrently at the same location. And even if we have no fast analyzers available, then we can also sample in flasks. I will come back to this using conditional sampling techniques. So as this is an observational or field campaign-oriented session here, I would like to say something about our site. So we, as I've said before, deliberately wanted to go higher than most eddy flux systems currently measure in cities. So we place the sensors, of course, on slim structures for the flow distortion effect, to minimize flow distortion effect. But on top here of a high-rise, this is the super site, so-called Hardau 2 in Zurich, in the city center of Zurich, where there's a mast on top of a high-rise building, or it's actually a cluster of 4 high-rise buildings, but this is the tallest building where we have an eddy-covariance site. This is located, Zurich is quite complex from the orography, but it's located within a valley. You see there's big railway lines to the north, but what I also wanted to point out with the map is there's a lot of green. You also see that in the view towards the lake here. There are big parks and street trees, and we will come back to this. Now, on top of this setup, we have a sonic anemometer, of course, and a typically used open path analyzer that measures CO2 and water vapor fluxes directly, but also we have all those inlets here. One inlet for the 7 gas species analyzer, one inlet for a fast CO, carbonyl sulfide analyzer operated by Helsinki University, and we have here something we call a relaxed eddy accumulation, so we can control over valves when samples are taken. I will show you some results from this super site in the remaining part of my talk. First of all, to get an overview, we have measurements here for 1 year from July 2022 to June 2023, and each of those little sections show you the mean diurnal course in a particular month. And so first of all, you see the fluxes are lower in summer, they go up in winter, but you also see the highest fluxes in winter are measured during the midday. But if we go here to June or July, you see there are the lowest fluxes measured during the midday. So you can already see some hint that this cannot be explained by emissions. Traffic is always highest during the midday, so that must be a hint to us that there is quite some significant photosynthesis going on. But let's look what else we can measure in addition to, again, a diurnal course. Now, over the entire year average and separated into winter and summer, we have in purple the winter and in green the summer measurements. And we can contrast this to CO fluxes we measure. So carbon monoxide. Carbon monoxide only comes from cars, from stationary combustion. But of course, respiration, even we do not exhale CO. So it is a clear hint to fossil fuels. Or we can also use NO and NO2, or we can combine the two to NOx, and we also have a hint for the source fossil fuel here. And if we look at the ratios, how they change over the seasons, you see that the CO2 is about 1.5 times higher in winter, the others not. So they are not going along. And also the diurnal course is different, so in the afternoon you have higher CO fluxes in regard just to the shape of the CO2 fluxes. So what we now can do is we can create flux ratios. So we can look at the ratio of CO to CO2. For every time step where we have an eddy flux, for every half hour where we process the fluxes, we can calculate a ratio. And we see this ratio is not constant because the two are not perfectly correlated. So, for example, in the early morning, the ratio is lower. And as we go into the mid-afternoon, it's higher. To make sense of this, we can also get the emission ratios from the inventories. So this is, for example, the emission factor for road transport. And this here is the emission factor for stationary combustion derived from the Swiss emission inventory for this, or specifically for the city of Zurich. And you see, essentially in winter, this is well between those spots. So it is more towards stationary combustion in the morning hours. You see here lower values. That indicates most of the CO2 presumably comes from the stationary combustion, and it goes up and it's nearly very close to the road transport value, so a lot of traffic signal in the afternoon. But if you look at summer, that's well outside. Now you say, maybe we've measured something wrong. Of course not, because in summer, the CO2 is also taken up by photosynthesis. So this simply lowers the CO2, and if you have the ratio of something divided by something smaller, the value you get out. And we can exploit this to look at the impact of the photosynthesis. And we can do that for different species. So here we have the flux ratio of CO2 at the bottom and the flux ratio of X to CO2 on the vertical axis. And again, the black dots are the end members from the inventory. We don't know if the inventory is actually perfect. And we see we are not on this line of the inventory. We actually have lower X values. And we also see here this effect in summer. So the triangles are the summer situation. But it's not a direct measurement. So we still want to have something really direct to distinguish between biogenic and the fossil fuel sources. So we can use carbonyl sulfide. Carbonyl sulfide is taken up in the process of photosynthesis. And if there are no sources in the city, which we are not completely certain, it should cause a negative flux the more photosynthesis happens. And there is some indication in the data. You see here in February, the carbonyl sulfide flux is more or less zero. It starts to become more negative, and that says there is some photosynthesis going on, and it's even stronger in the last part. Skip this one for the time, and I come to the most exciting last one, which is actually what we would like to measure are radiocarbon fluxes, because radiocarbon is the perfect tracer. There is no 14CO2 in, or there's no 14C in CO2 from fossil fuel sources, because it's so old, all gone, all decayed. So if we could measure radiocarbon fluxes, it would be perfect, but there are no fast instruments. It's way too low in its abundance. So we can only measure it in the lab by mass spectroscopy. But what we've done is we tried to measure it as a benchmarking, and we developed a relaxed eddy accumulation system that's shown on the bottom how this works. So you have the vertical wind. If you have an upwind, it goes into the upwind flask. If you have a downwind flask, and in between we have some kind of deadband that we exclude. And then we can look at the difference between upwind and downwind and calculate from that flux. There's a proportionality constant, beta, but this one we can infer from the total CO2 flux. How does this look like in practice? That's quite complicated. We have control valves at the bottom, and then at the top of the tower, and then tubes that go down, and we fill with very fast switching 2 tanks, an upwind and a downwind flask, and we can do that here for a total of 24 samples. So we have only 12 runs we can do. And I just, for the end, show you 2 examples that actually show it works. It's quite amazing that we can pick up here a time at 9 in the morning. That's the left-hand side. Here, this is the time series. And if we do the partitioning, it says in the morning, this is the total flux here in blue. And there's a small biogenic component, probably due to respiration. And here, and that's in the winter, you see this, the large fossil fuel component. And here is an afternoon case where we actually have a very close to zero flux, but we can partition it in a fossil fuel flux and a biogenic uptake. And that makes sense. We have now about 100 of those samples and can analyze them and put them in combination with the orders. I skipped this one. We stick to the time. So in summary, we can use co-emitted species and do flux measurements. They could provide additional information on the sources of CO2. So if we know the end members or the emission ratios, we can tell where it's coming from. That's our goal. We are not yet there. Or vice versa. If the sources are known, if we know it's only traffic, we can infer emission ratios and actually evaluate emission inventories. The COS fluxes, carbonyl sulfide fluxes, they show promise to separate photosynthesis out. And I showed you the first ever measured direct fluxes of 14 CO2 that have been measured. And I would say the partitioning is plausible. It still needs a lot of work, and it's intensely labor intensive, but it's quite exciting that we can do this. Next steps is to combine the information from those different sources, also together with footprint models and emission inventories, and do some kind of optimization between those. Thank you.